We will wait for a couple of minutes because I see that people are still joining, and then we can start the session. I hope you can all hear me and see my screen and all that. If there's any issues, please put it in the chat. Let's wait for 2 more minutes in case people are on the way. Today's lecture is about little bit of mathematics and some concepts which I think everyone should attend. So we'll wait for a few more minutes and then we can start the session. Uh, in the meantime, if anyone here has any doubts about the session so far, you can put it in the chat or you can unmute and speak, and we can discuss that before the session starts, or you can do it after also. But yeah, since we have some time now, if anyone has any doubt, you can raise your hand or put it in the chat. Okay, I don't see any questions, so we can, yeah, as I said, we'll wait for people to join. See that 8 people are there now, including me. Okay, it is like 6:05. I think we can start and let people join as they come in. So, right. So, hi everyone. Welcome to another one of these solving sessions. This is our 4th week in a row that we are having this. So, I think you should all be familiar by now. But in case there are any new people, my name is Zenia. I am a PhD student at IISc, and I work with compact stars and their evolution and modeling and so on. So I am one of the TAs, external TAs, who is handling the problem solving sessions of these course. And as I said, one sec, excuse me. Yeah, sorry about that. Um, right. So as I was saying, I am one of the external TAs who is handling the problem solving session of these course, and we have been having them every Monday at this time. So the goal of these sessions is to solve some problems which are similar enough to your assignment problem, so that while solving the assignment problems, it becomes easier for you. So apart from that also, we discuss a little bit of what was done in the class, and if anyone has any doubts, uh, if you want some specific topic to be discussed, I highly encourage you to mail me anytime in the week. Like this week, I think someone had mailed me asking about particulars of IAC and how to get there and so on. So you can also ask about things which are, not strictly related, academic things which are not strictly related to the course as well. I'll try to touch upon that at the end of the class, and I'll keep it up so that anyone who has a similar kind of question can easily access it, information about IASC and PhD and all that. Yeah, and of course these sessions are recorded, and the slides and recordings have been being uploaded by me once the session is over. I hope you are also receiving the same. If at all you cannot find the links, just go to my website. I have made a page where all the links are consolidated in one place. So this is about the sessions, and I think that, yeah, as I said, the goal of these sessions is to solve a few problems, but also it is meant for your interaction and your benefit. So if you want some specific topic to be discussed, like last week I discussed Maxwell-Boltzmann distribution because one of your friends had mailed me asking. So if someone has any topic like that they want to be discussed, which is related to the course, of course, then we can have a session to discuss that along with the problem solving. Okay, so this is just to inform you guys. And someone also brought up, just for as we are doing housekeeping, someone had mailed me. I don't know if don't remember the name, that there was some discrepancies in the last assignment and the problem solving session that happened. So I'm sorry about that. Like as I said, I'm an external TA, so I only handle these problem solving sessions. I don't really look into the assignments or their solutions. But I also checked it and I saw there's some numerical discrepancy. As far as I know, I think it is just some calculation error on the solution part or something. So just to make sure that everything is okay, I have reached out to the people who conduct the course, and I'll get back to you as soon as I hear back from them. So that is for the person who had mailed me earlier this week and was asking for a response. So yeah, I don't know if she's here, but I don't think so. But yeah, that's just about the course. So I just handle these sessions, and through these sessions, of course, the questions are the same, so there shouldn't be any difference. But there might be mistakes either on my end or their end or something. So that we will sort out and um, see. Okay, so yeah, that's all about the introduction part. So this week we are going to actually, so far we have looked at nuclear astrophysics from a primarily astrophysics perspective. We looked at various things, including, we had a flavor of what is observational astronomy, multi-messenger astrophysics. We looked at various astrophysical phenomena, like we looked at stellar evolution in some detail, how the exact stellar evolutionary cycle happens, and how compact stars are formed. We also looked at a little bit about the Hubble law and Big Bang, and sorry, nucleosynthesis in the universe, and so on. So this week onwards, I would say that we are now moving into more of the nuclear part of the nuclear astrophysics course. So yeah, so here we're going to go more into nuclear physics, and a lot of the things we discuss, you might think that where can I link this with astrophysics? But as I said, astrophysics is a subject where you interdisciplinarity is like the order of the day. You have various things coming together, and just to describe a star, for example, you need gravity, you need nuclear physics, you need orbital dynamics, you need so many different things, right? So from this week onwards, we'll be focusing more on the nuclear physics aspect of the nuclear astrophysics course. So today's class is going to be a little more mathematical than conceptual. Like we will be focusing on just one concept, which is reaction rates, but relating to that reaction rate and in its calculation, we have to calculate various other quantities. I think you know what kind of quantities I'm talking about, because this has been discussed in your this week's lectures. But yeah, I'll also go through it once more, because there are actually a lot of formulae to keep track. I won't be doing the detailed derivation of anything, but I want you guys to go and do it, because that will really help you from your understanding perspective, exam perspective, just all around, to get a flavor of nuclear reactions in general. So yeah, today's will be a little mathematical. I encourage you to have a pen and paper, calculator with you, so that today's problems will also be mathematical. So I want you to solve them with me. As I said before, hearing things just like that is very nice, but when we sit and do the mathematics only, physics starts to make sense to us, right? So yeah, so I that's just my whatever warning for today's class, you can say. So, with all that out of the way, this week we discussed the following things. I mean, there was this discussion of non-resonant and resonant reactions, Gamow factor and Gamow peak, and finally the astrophysical S factor. As I said, all three of these things are kind of related, in the sense that the non-resonant reactions is kind of the overarching theme of this week, and to calculate various things to the related to the non-resonant reaction, we have this cross section, reaction rate, Gamow factor, Gamow peak, all that comes into the picture. So one thing I will say is that, yeah, of course you have your YouTube lectures that professor has recorded, and also your various lecture notes and so on. But I also found this one lecture note online, and I found it kind of useful when I was preparing it, because I am also kind of new to this sort of study. I have not done detailed nuclear physics like this, so it was very interesting to me also to study along with you to give this class. So yeah, one thing that I will say is, you can go to this website or this PDF. This has actually all the topics that are discussed, and they do the detailed maths also. So I would say that once you watch this video, once you watch sir's video, you can watch one more thing. So sometimes it's useful to use multiple textbook or multiple sources for the same concept, because everyone describes the same concept in slightly different ways, and sometimes a different perspective might work better for you than the conventional perspective. So yeah, that's about this. So I always try that in all my slides I put the sources and extra notes and all that, so that you can go and look at my slides and click those links and go and have a feel for things. So yeah, whenever you see a link in my slides, try to go there and look at what I am linking to, because usually it's something that I found while making the slide which I thought was interesting and I wanted to include. So, right, so this is about the fourth week. So we can start the class. So as I said, we'll be solving various things relating to astrophysically relevant reactions from a nuclear physics perspective. So before we start doing the questions, I thought it'd be good to have a recap of the concepts, because as I said, there are a lot of mathematics involved. So I would say that if you are yeah, if you don't follow all the maths, it's fine. At the first, if you don't follow, it's fine, but try to do the maths yourself at least once. Of course, in the exam you might not be able to do it, but you might have to memorize at least partly. But I would say that at least once before the exam you should sit and do the derivations, then only it will be making sense to you. Otherwise it will be like you have plugged from the air and you're doing, it's just a machine, right? You have a machine, you're putting your numbers in, getting some number out. So physics should not be like that. You should have some context for what is happening. So yeah, a very long introduction today, but we can go to the lecture. So so this is going to be the central equation that we are going to look at, which is the reaction rate per particle. And you can see that our friend cross section sigma, and v, which is the speed. And last week I showed you a picture where it was like, because nuclear physics is so deeply quantum mechanical, when it's you have to think of it like a bullet hitting a target, right? It's not only the size of the target which matters, but also the speed of the bullet, which is not a classical concept. In classical mechanics, only the size of the target matters, how big the target is. But in quantum mechanics, the size of the target and the speed of the bullet are kind of interlinked through Heisenberg uncertainty and so on. So we should make sure that we have both the terms, and you will see the sigma v pop up everywhere, because that is a reaction rate, and that pops up in there's a reaction rate per particle. So we are currently very interested in non-resonant reactions. So the concept of resonance should be familiar with you. Resonance is when a process which is so when something resonates with you, that means that it is meaning something to you, right? So a resonant process is something which peaks at a particular energy or has a strong energy dependence. Non-resonant reactions means there is no sudden change in the cross section as a function of energy. This does not mean that sigma is not a function of E. You can see that sigma is still a function of E, which means it varies, but it is not like there is a zero sigma everywhere and then a sudden jump in the sigma and then a zero sigma everywhere. So this is resonance you would have seen in terms of your sound waves and frequencies, right? Resonant frequency and all. So it's same kind of concept. In resonant reactions, there are certain cross section where the reaction rate peaks, and that's where most of the reactions happen. So in resonant reactions, it becomes very easy to say this is the energy where the reaction is happening, and other energies reaction is, we can consider approximately the reaction is not happening. But in non-resonant reactions, how do we answer that question? What is the maximum or what is the optimal energy for the reactions to take place? So to answer that only, we need all this calculation of Gamow peak and Gamow energy. So the point is that if I had a resonant reaction, that already by default tells me that this is the energy where everything is favorable. Whereas in a non-resonant reaction, such a straightforward answer is not there, and that's why we have to work a little bit for it. Okay, so you can see that unless we know this value of sigma e, or the functional form of sigma e, we cannot solve this integrand. So our efforts today will be to solve this integrand, and for that we need to find the how to characterize sigma e. And we know that it's not resonant, so there is no particular energy where it's significant. It could be significant at multiple energies also. So we have to see where the reactions happen in a few different ways. So the first and foremost, we are dealing with nuclear reactions. So there are, when you bring two nuclei together, there are two forces which happen. So there is an attractive force, which is your attractive nuclear potential, and then there is the Coulomb barrier. So there is basically the force of electromagnetism, and there is nuclear force, right? So one question that you might have is that like charges repel, right? But in a nucleus, we know that we have many protons, multiple protons put together in a small space. So why aren't those protons repelling and flying away from each other? So the answer is that the protons in the nucleus of this are held together by a force called the nuclear force, the strong nuclear force, and this is much stronger than the Coulomb force. The Coulomb force is basically the electromagnetic force that causes repulsion. So there are two forces here. There's a repelling force, which is a Coulomb force, and there's an attracting force, which is a nuclear force. At the distance of a nucleus, it is a nuclear force which wins out. But as we go to higher and higher separation, we see that the Coulomb force is more significant. So there is a transition between the repulsive part and the attractive part, and in between you have a Coulomb barrier. The Coulomb barrier is basically when you take two magnets together. Okay, so you can think of it in terms of charges, but since we cannot hold electrons in our hands, you should actually think of it as charges. You should think of it as two protons or two electrons. But since none of us have held single protons in our hand, it might be difficult to visualize. So I'm just explaining in terms of magnets, right? So imagine you have two magnets. So when I bring two what is it, same polarity magnets together, you can feel the force that is stopping you from getting them in between, right? So that is kind of like a potential barrier, and that's exactly what happens when two protons get together. When two protons get together, there is the Coulomb force which does not want them to be together, because as we all know, like charges repel. But if the proton has enough energy, you can see that it can overcome this barrier. It's just like a wall, right? If we are high enough, if we jump high enough, we will get over the wall. Similarly, if the proton has enough energy, it can overcome the Coulomb barrier and it reaches the attractive regime. And once it's in the attractive regime, the attractive force is much stronger and they stick together and they form a nucleus. And that's why it's very difficult to break apart a nucleus, is because a strong nuclear force is really very strong. So the point is that now, how do we get the particles to be over the barrier in the first place? So one thing is what I said, if I have a very high wall, I will jump over that wall. To jump, I need energy. And similarly, particles also need very high energy. And we know that energy is directly related to temperature. We know E is kT. That's something that we have done over and over again in the course. So basically, that means I need to be very hot, right? So if I need two nuclei to be fusing, I need that amount of temperature which is equal to the Coulomb barrier. I need to jump at least higher than the height of the wall, otherwise I'm not going to get to the other side. It's a similar kind of concept here. So you can see that this is the Coulomb force. I think you're all familiar with it. And here, E squared has been written in such a way that it already has all the units of energy and centimeter put into it. So you can see Z1 and Z2 are the atomic numbers. Basically, it tells you how many protons are there, right? Because between two protons, if it's just two hydrogen atoms, that's effectively two protons. So between two protons, I'll just have E squared by R. But if I have three protons, then each of them will have repulsion between each other and so on. So we have to consider like that. And that's why we have to multiply the atomic numbers, because that tells you exactly how many protons there are in the system. Each proton has a charge of E, and you have to see the separation between them. So to overcome the Coulomb barrier, as I said, we need very high temperature. And you see that for proton-proton reaction, which is basically hydrogen fusion, as I said, hydrogen burning is basically the driving force of hydrostatic equilibrium in the sun, as we discussed in great detail in, I think, the first lecture, right? So you can see that for proton-proton reaction, this wall's height, if you think of it as energy, is actually 550 kilo electron volt. You can all do this exercise, it's very easy. And then you know how energy and temperature are related. So if I convert this to temperature, I see that I get something like 10 to the power of 9 Kelvin, something of the order of 10 power 9 Kelvin. But I know that the sun's energy is around 10 power 7 Kelvin. So how is fusion happening? How is the proton able to overcome this wall if its energy is only around this much, right? So for that, we turn to, first let's look at something that we looked at last week, right? When I say the sun's energy is around 10 power 7 Kelvin, that does not mean that every particle has 10 power 7 Kelvin. As we saw last week, particles in a gas or in a star or in a stellar plasma are distributed with variety of temperatures and variety of energies. right? And that is what is called the Maxwell-Boltzmann distribution. So this, the peak of the distribution might be 10 power 7 Kelvin, because most of the particles have 10 power 7 Kelvin. So if I'm going to measure the temperature, I'm going to get 10 power 7 Kelvin. But you can see that there are a very few particles who have very high temperatures, very few particles which have very low temperatures. So maybe it's like those high temperature reactions alone are, contributing to the burning that is happening inside the sun. So the problem is that based on temperature alone, there is actually close to a zero chance for the fusion reaction to happen, and we can actually show this. And for this, again, we have to use the Maxwell-Boltzmann distribution. So as I discussed last week, Maxwell-Boltzmann is basically a probability function. It tells you the answer to the Maxwell-Boltzmann distribution is the answer to the question how many particles exist which have a speed in this value. And you know that speed, temperature, energy, they are all related, and we can convert one to the other. So when I say, okay, I have a distribution which peaks at 10 power 7 Kelvin, but what is the chance that I have some particles which have 10 power 9, or whatever the exact number is, 6.4 into 10 power 9 Kelvin. So you know that you can see that if I use the Maxwell-Boltzmann distribution function, I can find out what is the probability that a particle has, 550, and then I can find out what is the probability that a particle has, 0.86. So 0.86 is the corresponding value for 10 power 7 Kelvin. And if I find the probability, given that the relative probability between these two, I see a factor of 10 to the power of minus 275. So this is an unimaginably small number. For all practical purposes, this is zero, right? So this is 0.00000, like 275 zeros and then a 1. So for all practical purposes, this is a zero. It's clear that if reactions are happening with this probability, that we will never have sun burning, and sun should have collapsed long ago. So again, the question comes, sun's energy is around 10 power 7 Kelvin. How is fusion happening? And the answer is encapsulated in this picture, which is quantum tunneling. So again, quantum mechanics keeps coming up in this course in one way or the other. And there's very simple reason is that we are in the regime of nuclear particles, nuclei, which are very small particles. As I said, that is the exact regime where quantum mechanics becomes very important. So just to explain this picture, this is something I got from Wikipedia's media section. So you can see that, don't worry about all this, but basically you have a barrier, right? You have a wall. So this is exactly my wall. This is a wall I need to jump in. Now my particle, you can see that you can think of me as, being represented by this wave function, because quantum mechanics says that we are all, described using wave functions actually. So you can see that the wave function has energy between these gray bands. And classically, if I'm going to throw a ball, or if I'm going to if I'm going to throw a ball like this, it's never going to cross this wall. I have to throw a ball with energy such that it can go over the wall. But because quantum mechanics is probabilistic in nature, you can see that as the wave particles approach the barrier, most of it gets reflected back. 90% of it gets reflected back. But there is a small fraction of particles which actually penetrate the barrier and are going to the other side. So this is why quantum mechanics is so profoundly weird to us, because it gives us solutions like this, right? This is like if you throw a ball at a wall and it went through the ball. So this is exactly what is called quantum tunneling. And you can read a little bit. This is a link where people are trying to explain how the conceptual understanding is. It's not very important for you at the moment, especially if you don't have a very good quantum mechanics background. Don't get worried about the details of it, but essentially we need to solve the Schrodinger equation to get the wave function and probability. So just like how in classical mechanics you have Newton's laws, and based on Newton's laws you can write kinematic equations, based on kinematic equation you can write trajectory, you can track a particle. If I know the particle is here, starts off at x and t, and if I know the velocity, I know that where it will be at some time t plus T1 or T2 or T3, right? Similarly, the evolution equation for quantum mechanics is called the Schrodinger equation. It's a very famous equation. And here, as I said, we don't describe particles based on their position and velocity, because there is something called the Heisenberg uncertainty principle, which tells us that simultaneous um, measurement of position and velocity is impossible. So we describe in terms of some mathematical functions called wave function, and the wave function is directly related to probability. So here you are seeing a kind of description or a animation of that, and you can see that the wave function evolves in such a way that there is always a small probability that the particle gets to the other side. So it's not something crazy like the whole wave packet is going to the other side. You can see 99% of it is coming back. It is a very small percentage which actually tunnels. But this small percentage is so important to us when it comes to the astrophysics point of view, and when it comes to hydrogen burning. So just to remind you, the issue that we have is there is this Coulomb barrier, and we have just calculated the Coulomb barrier for H proton reaction, which is basically hydrogen burning, which is how the sun is powered. But we found that the energy is too high for the protons inside, for the sun to fuse hydrogen. So now we are going to see if this sort of quantum tunneling can help us. So I hope everyone is okay with this concept. I said a lot of things relating to quantum mechanics and Heisenberg uncertainty principle, Schrodinger equation. So these are all things that are explored in a proper quantum mechanics course. So I would say that for now you can understand it at a um, what to say, like surface level. But if you are interested in pursuing physics further, you should take quantum mechanics courses, and you should like look at all of these things in detail. And yeah, but this is not exactly the platform for that, so I'm not going into much details. I hope this is okay. If anyone has any immediate questions, you can please put it in the chat, otherwise I'm moving on. So again, so now if we solve the quantum tunneling problem, again the Schrodinger equation is an equation that is like a differential equation in psi is the wave function. And if you solve for it, you get an expression for the wave function, and the wave function is directly related to probability. So just like how I solved probability here based on Maxwell Boltzmann, which is a classical distribution, here also by solving the Schrodinger equation I get another probability. So I'm going to compare this quantum tunneling probability and the other probability, which was this this is the Maxwell Boltzmann probability, and see what gives me a better chance. And I think you guys already know the answer because this exercise has been done in the class. But basically, if I calculate the probability of particle being at the classical radius, so this is basically your classical radius, this is your nuclear radius, and the particle has to tunnel between this barrier, right? So you can see that there is some exponential function which has a dependence as a square root of e, and this you can write in terms of some b function. Okay, so for a pp reaction, you can see that this probability gives us a chance of 10 to the power of minus 10, and this exponential factor is exactly what is called the Gamow function or the Gamow factor. And you can see that 10 power minus 10, although it's a very small number, it's huge when we compare to 10 power minus 275. So this is how reactions in the sun are taking place, because there is a 10 power minus 10 chance of quantum tunneling which is happening, which is enabling these reactions to take place. So even though this is a small probability, it is significant enough because we have so many protons in the sun. So even if this many of them are taking part in the reaction, it's still significant that it contributes to hydrostatic equilibrium and nuclear fusion and all that. So this is the idea about quantum tunneling. So now we have looked at how temperature is not adequate, and we have quantum tunneling. Now the other concept that's very important in the nuclear physics point of view, again I hope you all understood that argument with Coulomb potential and quantum tunneling. I went through it, little quicker because I think it has already been covered in your lectures. But if you have any doubts, you can ask me. Essentially, it is a very simple thing. Is we are looking at the probabilities, and we see that one process is heavily favored over the other. So we can then conclude that this is the process by which the particles take place, fuse in the sun. So now we are looking at the astrophysical S factor. So you can see that this is again going back to the beginning of the lecture. As I said, our whole goal was to calculate this reaction rate, because in nuclear physics, what we are most concerned with is this reaction rate, right? So as I said, the big unknown here, we kind of know the temperature, we know what is the energy should be, but the big unknown is how the sigma or the cross section varies with the energy. And for that only we are trying to look at these various processes which are happening, so we can get an idea of what is the exact cross section that is taking place in the star. So you can see that Now we have an idea that cross section varies as b by root e, which is from quantum tunneling, which is the dominant process that we just now calculated. We also know that classically the as I said, when I look at the cross section, what is the basic definition of cross section is the size of the target. Remember my bullet and target analogy. But again, as I said, because this is a quantum mechanical regime, the target size does not remain constant, but because of the wave nature duality, target size is linked to the velocity of the particle, or in this case, the energy of the particle. So you can see that I'm taking it as pi length squared, basically the circular cross section, but here length is described in terms of lambda, which is the de Broglie wavelength. And the de Broglie wavelength, of course, as you all know, h by p, and h can be written as 2me, root 2me. So you can see that lambda is basically proportional to 1 by e. So we see that sigma e is proportional to 1 by square root of e times e. And if we want to remove this proportionality constant, then we can introduce another energy dependence, and this is exactly called the astrophysical S factor. So again, in physics, many times it becomes important to distinguish mathematical convenience from physics, right? So here the astrophysical S factor does not add any new physics to the problem. Whatever the astrophysical S factor tells us is already told to us by cross section already, right? We don't really need another term, except that the astrophysical S factor is there more for our convenience, for our mathematical convenience. Because as you know, this is a non-resonant reaction. There might be, or even it could be resonant, and the problem is that sigma is very 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 badly dependent on the energy and its variations. You can see there's an exponential dependence on energy and also a 1 by e dependence. So as e changes a little bit, sigma will change a lot, whereas S is what I get when I factor out all those energy dependence and just look at the basic dependence, removing this quantum tunneling probability and the lambda probability and all that, and just looking at, for a fixed lambda and for fixed quantum probability, what could be the cross section of that reaction. So this kind of takes away all that variation that is coming because of the variation of quantum tunneling and the variation of the cross section with energy, as I sorry, cross section size with energy, that bullet and target analogy. So that's why the S factor is useful. So the X factor is a more reliable, or not even more reliable, it does not vary so sharply with the energy that it becomes a little more easy to work with. So again, I'm saying, like in physics, not only in astrophysics, many parts of physics, you will find things which are purely mathematical, and you have to be very careful to understand that here we are not doing any new physics. We are not, reinventing the wheel. We are just doing some mathematics, which is equally important for us to solve problems, right? Getting concepts and writing equations is fine, but to solve those equations, we usually have to do some tricks, and those tricks are, sometimes they are purely mathematical, sometimes they have insight of physics also. So this is a kind of idea of astrophysical S factor. So once again, I'm flashing the first slide because I want to like show you that all of this is connected. Because at times what happens is we might learn this and we might see this as 5 different formulae, but actually what is happening is there is one formula and there are 4 parts to that formula which are all feeding into one master equation. Here, this is my master equation, this is the equation I want to solve, right? So now what and all did I do? Just to recap, I wanted to look at how to solve this integral. I said, okay, what is problematic is sigma of E, because I don't know how sigma varies with E. I then thought, okay, what is the reaction which is actually happening? It is a nuclear reaction, and nuclear reaction has 2 parts, which is an electrostatic repulsion and a nuclear attraction. So I know that the reaction will only happen if I overcome the Coulomb barrier. So first I have to see what is the process that helps me overcome the Coulomb barrier. I found out that it's not just temperature being high, it's not just these energetic particles, it's in fact quantum tunneling that we have to invoke. So then based on quantum tunneling and based on cross section physics, I was able to find what is the dependence of sigma of E. So now I can go back to that first expression which I showed in the first slide, and I can plug everything in. Plug everything in means just sigma of E, which we just now calculated. So this expression I am putting here, and you can see that this is the sort of expression I get. So okay, so now this is This is a nice expression and I can solve it once I know E and T. But more interesting is for me is not, I don't want to know all the places where the I don't want to, it's not very useful for me to know the entirety of the sigma V. uh, I'm more interested to know what is the peak energy at which the reactions are taking place. So remember, I told you we are looking at non-resonant reactions. So the reaction cross section is not strictly, very sensitive to any particular energy in the distribution. But nevertheless, there should be a maximum value, right? There should be a peak where the reaction is happening most favorably. So to find that peak, as you all, as we did last week to find, for example, the most probable velocity, we again use the differential and set it to 0, and we find that this is the expression. And of course b here is just, where did I write b? Yeah, this is b. There are so many factors. If I substitute back b and substitute back all the values of the factors, you can see that I get this expression, and this is exactly what is your uh, energy, right? So this 1.22 keV and T6 is got by, substituting all the values in terms of the correct values, and you get this kind of expression for the energy. So yeah, a lot of what we're doing here in nuclear physics, and so far what we have done is look at collections of particles. As I said, we are looking at statistical distributions of a large number of particles. So we, in that, we cannot be interested in what proton number 500 and proton number 750 are doing, right? We have to be interested in the properties globally of the distribution. So that's why Maxwell Boltzmann exists. That's why these kinds of things exist, because we get to know, okay, what are the particles that I should focus on? The particles which have energy of this is where the maximum reactions are happening. Because again, I cannot look at all 1 million protons in the sun at the same time. So that is the kind of idea that we are doing philosophically. So this is about the maximum energy where the reactions take place. And actually this is more of an energy window. It is not just a single part. It's not that we have that particle and their reactions happen and nowhere else reactions happen, right? It is like a, there is a region where the reactions are happening favorably, and that is what is called the Gamow peak. So the Gamow peak is the answer to the question, what is the energy window where the maximum number of reactions take place? So you can see that here both the processes that we have considered are shown together. So one is, there is a Maxwell-Boltzmann distribution which shows that energy is, which varies exponentially with energy. So there are a lot of particles which peak at lower energy and so on. And then you also know that there is a tunneling through a Coulomb barrier, and that tunneling becomes more favorable if you go to higher energies. So Maxwell-Boltzmann is something that peaks at a particular value, and then below that value and above that value there are less probability. But tunneling is something that keeps on increasing as we go to higher and higher energies. So there is a region between both of them where the Gamow peak relies. So basically, if I check here, then I know that, yeah, I have energetic particles. I have a lot of particles, right? Because Maxwell-Boltzmann tells me about how many particles I have. So this tells me that, okay, I have a lot of particles, but none of them are, undergoing tunneling. You can see that tunneling probability is very low. So even though I have a lot of particles, none of them are going to contribute to my fusion. So again, as we just now saw, what ultimately contributes to fusion is your quantum tunneling. So here, even though I have large number of particles, there is no tunneling happening. On this side, I see that there is a good possibility for tunneling. So lots of particles can tunnel. But where are those lots of particles? There aren't any particles here. The distribution has died down. So I have to go to that region where there is a good chance of, there is, somewhat chance of tunneling also, and there is also some number of particles, so that both of them can match up together. And this is the region that we call the Gamow peak. Okay, so the Gamow peak is a Gaussian function. It's a normal distribution or a Gaussian function, and that's a function that comes up again and again in statistics. So you can see that these are what Gaussian functions look like. You can see that they have this general form. Here sigma is basically what's called the variance. The variance, sigma squared is called the variance. Sigma is the standard deviation. So it is basically the width of this bell curve. So this has a lots of names because this Gaussian curve is one of the most famous curves in all of statistics, physics, maths. It comes up everywhere. So I think most of you should have seen this kind of thing before. Basically, it's an exponential of this form, and this is the normalized Gaussian distribution. So here you can see that, as I was saying, sigma is the standard deviation, which is basically the width of this curve. So you can see this is the width, and then mu is basically the mean. So that means where it is centered. So you can see this red curve has a mean of 0. So you can see that it is centered about 0 and it has a variance of 1. So that's why you can see that from 0 it goes to around 1 if you go to the full width half maxima. Again, I'm not going to very much of details because this is, statistics is a course of itself. But if you basically draw a line like this, you can see that it goes from -1 to 1. Similarly, for the green curve, you can see the center is at -2, and then if I draw a line, you can see that I go from um, zero point 0.5. So it's like -2.5 to 2.5, and this one has a very large variance because it's like a very well distributed. But then how am I calling this a Gaussian distribution? I mean, by seeing it's a Gaussian distribution, but I saw that the Gamow function is just exponential. It is not a square, right? Exponential minus square. So actually you can sit and you can do the maths. Again, this is one of the things which I was telling, is that there is a lot of maths involved. I didn't sit and do all of them in this class because um, I think it's been explored in the class, and also that's not very useful. Watching me solve it is not as useful as you doing it. So you can actually sit down and approximate this function as a Gaussian. So that when you do that approximation, you will get this kind of thing, and you can see that you get some sort of E0, and you can, when you compare these two, you can actually understand. So E0 is your mu here. So mu is basically your centered value. So that is the value where the maximum probability, oh sorry, yeah, maximum probability or maximum value lies. So that's your E0. And on, yeah, the peak of the curve basically, and del by 2 is your width, which is your sigma here. So the width is, so this, you can think of this curve, but this would be E0, this will be del by 2, del by 2 minus del by 2. So the total width is actually del, right? The photo, because you have del by 2 on this side, del by 2 on that side, so the total width is like a delta. So that's how you, and then again, if you put in the delta values when you are doing this function, you will get this kind of value for delta. Again, these are probably the expressions that you will finally have to keep in mind, because it is not very practical to go and do, I don't know how your exam pattern will be, but may not be practical to go and derive everything every time. But nonetheless, instead of just memorizing, I would say that before the exam, even after this class, sometime this week, sit down and do all the steps of these, so that at least once you have done everything, right? You don't have to do it in the exam, and you won't need to do it in the exam, but it'll be good if you sit down and do all the steps. And by the way, this, if you calculate this integral between 0 and infinity as is given here, you will get delta root pi by 2. So Gaussian integrals are very famous. There are a set of like very standard values for Gaussian integrals. If you have taken a elementary maths, not elementary but like college level maths course, you should have come across it. So finally, again, a matter of notation. So again, once again, I'm emphasizing, from this step to this step, I had some new physics, in the sense that I have this quantum tunneling probability which is put in, and that's my new physics. After that, whatever I have done has all been mathematics, right? This is my physics step. After that, I rewrote this in terms of this. I found the peak energy, and then we rewrote it as a Gaussian. Writing it as a Gaussian is not going to help me understand any deep insights of the physics, but it really helps me when I'm looking at the when I'm doing the calculation. Like now I can immediately tell you what is the width of the Gamow peak, which is not straightforward when I look at this function. By looking at this function, it is not, if I ask you what could be the width of the peak, it's not straightforward. But recasting it to a Gaussian function helps us, because Gaussians already have well-defined functions which tell us how how wide it will be and so on. So, and finally, another approximation that people do, or another recasting that people do, is that they introduce a new variable tau. Again, no new physics, this is just me rewriting it in another variable instead of E0. And when you rewrite it again, if you put all the relevant quantities here, you will see that finally sigma V as a whole will depend on tau squared to the power of e minus tau. And the reason that this is interesting is because tau actually contains all the temperature dependence that is existing in the function problem. And now I just have to worry about tau squared and e minus tau, and the rest of them are normalization factors. So as I said to you last week also, we have to normalize these functions, because at the end of the day they are probability, or this is not really a probability, it's a distribution, but finally it has to sum up to some, this is a reaction rate per particle, right? So we have to think of it in that way. So that's why having the temperature dependence have encapsulated in two terms is very interesting, and that helps us to make our problems easier. So again, there is physics insights, there is maths insights. These last few slides have been maths insight. So there is a lot of things which was discussed. So just before moving to the questions, I will just do a quick recap. So essentially, we are looking at the reaction rates of non-resonant reactions. What are non-resonant reactions? They are reactions where the cross section is not very strongly dependent on the energy, in the sense that there is no sudden jump or delta function kind of thing in the energy dependence of the cross section. So then how do I now describe where the maximum reactions are taking place? For resonant reactions, there is a certain resonant energy where the reactions are taking place at their maximal value. It is not the case for non-resonant reactions. So how do I figure that out? To figure that out, I have to basically find where is this reaction rate peak. When the reaction rate peaks, that means that I am having a lot of reactions at that point, right? So to find the peak of this reaction rate, I have to then know what is the dependence of sigma of E. Sigma of E is a cross section. So how do I find the dependence of the cross section? Well, I have to look at what are the actual physical processes which are happening in the system that we're studying. The system that we're studying is of course stars and stellar plasmas, where there is nuclear fusion. And I know that when nuclear fusion happens, there are two competing processes. One is your electrostatic repulsion, and the other is the attractive nuclear force. So I need to reach this region of the potential where the attractive force is dominant and the Coulomb force is not dominant. So for that, I have to overcome the Coulomb barrier. I have to jump this wall metaphorically. So there are two ways in which I can jump the wall. One is to have enough energy that the wall does not matter to me. But as I saw, that energy is too high. It's too much high that the sun would never fuse anything if it was just reliant on this process. And for that reason, and we saw that even if we consider the most energetic particles in the sun, which are at this part of the Maxwell-Boltzmann distribution, the probability is so small that is effectively zero, and this kind of probability would never keep the sun stable. So then I know that, okay, I still want to find sigma of E. I know that this is not the thing that is contributing of sigma of E. This is not what's causing the reaction. So what is causing the reaction? So then I look at my quantum tunneling, which is happening, and you can see that there is a small probability, very small probability, that quantum particles can tunnel through potential barriers, and for that we need to solve the Schrodinger equations to get the wave functions and probabilities. So again, I have not done that here because that is quite advanced. I think that if you do any sort of quantum mechanics course, this is one of the first problems that you'll solve. So you'll solve particle in a box, then you'll solve particle going through a potential barrier, and there you will exactly know what is happening. But for now, you just need to understand it at this level, which is that there is a wave packet which is traveling rightwards, which has a mean energy given by the gray bars. When it hits the barrier, there are two things that can happen. It can either reflect or it can transmit. You can see that classically it would never transmit because it doesn't have enough energy. But quantum mechanically, there's always a small probability that a small portion of the wavefront will get transmitted. And this is exactly what is called quantum tunneling. And even though it's only a small portion of the wavefront which is getting transmitted, we find that that small portion is significant enough that it gives us a probability of 10 power minus 10. Small, but this Gamow factor is not so small when we compare to 10 power minus 275. It gives us a quite a good what can I say? Quite a good uh, improvement when it comes to the whole process of nuclear fusion. So now I have the kind of what the reaction is happening because of. So because of that, now I have my sigma of E, I am in a position to start to write sigma of E. So I know that sigma of E, there is two contributions to sigma of E. One is of course the probability that the reaction happens in the first place, and also I know that sigma of E is roughly the cross section, which means it has to do something with area, and here the area in question is energy dependent, which is my de Broglie wavelength. So when I put everything together, I get this expression. And to make my life slightly simpler, I also put in the astrophysical S factor, which is encapsulates my which basically puts my proportionality to an equal to. Finally, I can go back to the beginning of the thing, which is where I sat down and I said, I want to know how the reactions happen, and I want to know the maximum energy, where the maximum reactions happen, at what energy do the maximum reactions happen. So when I put in all the values and I do some maths, I can see that the maximum energies happen at this particular energy value. And this is of course called the Gamow peak. It is where both of the processes that we considered have a good amount of value. There are enough particles and they are energetic enough to undergo tunneling. So here there are lots of particles, but they are not energetic enough to undergo tunneling. Here there is enough energy for tunneling, but there is not enough particles. So we have to kind of reach the middle ground, and that is where the Gamow peak lies. And you saw that it is useful mathematically and not physically, but mathematically, to recast the Gamow peak in terms of a Gaussian function, because Gaussian functions have well defined standard deviation and distribution and so on. So we can extract many properties easier. So if you do, and I highly encourage all of you to do the mathematics and find out how this can be recast to a Gaussian function, which eventually gives me the width of the distribution, and I can also encapsulate the temperature dependence in terms of a new variable tau. So this is basically about non-resonant reactions, cross sections, reaction rates. A lot of things have been introduced, but hopefully you understand that everything is kind of connected to each other, and there is some motivation to go from one step to the other. It's not that I'm calculating S factor on one side and then I'm calculating Gamow factor on the other side. Everything is linked to each other, and everything is finally to calculate the reaction rate, which is what is important when we look at the nuclear physics perspective, what is happening. So I hope this is all clear to you. I know this was covered in your class also, but I thought it'll be a good idea to look at it again, because there's a lot. It was a little confusing. It was confusing to me also at first. So we have to keep track of what's happening and why each step leads to another, and why all these quantities are important in the first place. So I think whenever you do physics, it's good to have that big perspective, big picture perspective, which is that why am I doing this all in the first place? It is all to calculate this one quantity, the nuclear reaction rate. Okay, so hopefully you see all that. I'll just stop for 5 minutes or 2 minutes now before we move to doing problems, so that if anyone has any questions, immediate questions, you can ask me. You can either unmute or put it in the chat. Okay, I don't see any questions. I hope you're all following what's happening. So then, yeah, okay. So I'm just seeing the chat on my phone in case I'm missing any questions. Yeah, I don't see any questions in the chat. So then we can move on to doing problems. So today's problems are all going to be kind of mathematical, and they're all going to be based on these kinds of all these formulas that we have discussed so far. So please keep a calculator ready like last week. I think I have flashed all the relevant formulae, so it should be very easy for you to solve the problems. But yeah, some of them require multiple steps, and this week the problems are such that the answer of problem 3 and 4 might come in problem 6. So it's better if you do all the problems together, so that you can use the previous values in the next problem and you don't have to start from the beginning every time. Okay, so I hope that makes sense. So we're going to go to the first problem. Okay, so this is a direct problem. I think you should all be able to do it. At stellar temperature, T6 is equal to 15. Again, you should be familiar by now. T6 here means that T is 15 times 10 to the power of 6 Kelvin, right? So yeah, so there is a temperature of 10 power 15 times 10 power 6 Kelvin. They're asking what is the Gamow peak for the proton-proton reaction. So I already showed the formula. This is a direct substitution question. I want all of you to solve it and put it in the chat. So I see that someone has already answered. That's very good. Let's see. Someone has already answered. Others also please attempt the question and answer it. This is a direct substitution and you should be able to do it pretty easily. I only see one answer in the chat. Okay. But yeah, please, I'll give you some time so that you can solve. Sorry, is there a question? Hello? Okay, I think someone unmuted by mistake. Okay, I'll give you some time so that you can all solve the question before I move on. So yeah, I want more people to answer in the chat and then I'll move on to the answer. Let me just check the... Is there a question? Is there any question? Okay. I don't think there's a question, so I will just move to the... If you have any question, please interrupt. But if you're not asking a question, please switch off your mic. It's kind of distracting. I only see two answers in the chat. Please, others also put the answers in the chat. Otherwise, it's difficult for me to move on to the next question. I hope everyone is solving the question. Is there anybody who does not know how to solve this question? If you don't know how to solve this question, you can put that also in the chat. Then I can help out. But yeah, I think this is a direct question. You should not have any trouble to solve this question. I'm waiting for more people to put answers in the chat before I move on further. There are only two answers. Is there anybody who does not know how to solve this question? Please put it in the chat. If you don't know how to solve this question, there's no issue. Okay. I see one more answer. I think most of you are agreeing that it's C. But there are like 15 people here. So I want to see at least two more answers before I move to the next question. So please solve the question. Again, these are sessions which are held for you. The reason I am not solving them is because if you sit and solve, it's going to be much more easier for you when it comes to exam and all that. So you don't have to practice separately. You can practice now and that will actually help you a lot in your exam. Others? I see three answers. All are C. Others? Any answers in the chat? Or you can unmute and say. Okay, I think I hope the rest of you know how to solve it. I mean, if anyone doesn't know how to solve it, again, I'm saying to put it in the chat. I'm just moving to the answer because we have other questions to get to. But I am kind of disappointed. I want all of you to put their answers in the chat. Otherwise, there is no use of conducting this session. So the answer is C. Good for all of you who did it. Very good job. And this is the process. As you know, that energy at the Gamow peak is given by this formula. So this is actually that B by root T formula. Or I think in the class, the formula was written in terms of exponential of 2 pi eta, right? Something like 2 pi eta was the Gamow factor. So both of them are the same. I have just written the dependence in a slightly different way. It's just a constant. Again, that is mathematics. That is not physics, right? The mathematics is whether I write as 1 plus 2 or 2 plus 1, it is still going to give me 3. Similarly, I have written as b by root t. Your professor might have written it as 2 pi eta or something, the Gamow factor. But regardless, when you substitute that into your rate equation and then you find the maximum peak, you will find this kind of expression. And here you saw that it's a proton-proton reaction. So because of that, the atomic numbers are both 1. It's atomic number 1 in both cases. This is the reduced mass. So right, I should have explained. I think you all are familiar with the concept of reduced mass, but for in a simple way, if I have two particles colliding with each other in a central force, for example, if I have Earth going around the sun, I can, or any collision between two balls or something like that, I can consider it to be effectively a one body problem by using something called reduced mass. So here, instead of considering the motion of two particles, if I use the concept of reduced mass, I'm effectively looking at a one particle which contains the information of both of them. And the formula for reduced mass is m1 m2 by m1 plus m2. Here both of the particles are protons, so it becomes mp squared by 2mp, and that becomes 1 by 2. And of course T6 is given in the question. So this becomes a direct substitution. 1.22 1 1, this is 0.5 and this is 15 squared whole to the power of 1 by 3. So this is a direct question. I think all of you should have got it. So whoever has not solved it, is it clear to you now, or do you have any doubts? Why didn't you put the answer in the chat? I mean, is there any doubt at this point? Please put it in the chat also, because then only it makes sense to solve the problems, only if you understand them completely. So if you have any question at any point, please interrupt me either from the chat or raising your hand and talking or something like that, because that will help to make this more interactive. Otherwise, this is just like you watching the recorded videos which are already provided to you by NPTEL. So this is supposed to be a live session where we can kind of discuss everything. So please feel free to interrupt me and don't feel shy to ask any question. So I think this slide explains everything about how to do this question. So I think no one should have any questions. I'm moving forward, but again, if you have questions, please interrupt me. So this is the next question. So when something is written like this is basically a reaction. So deuteron plus proton is giving a gamma particle plus a helium-3 nucleus. Or helium-3 particle, whatever. So you can see that this is a nuclear physics way of writing. D plus P gives gamma plus He3. That's how we usually write it. So yeah, the dp3He reaction of this Q value has been measured at center of mass energy above this value. The Coulomb barrier for the dp reaction is. Now here there's a lot of quantities which has been given, but really only some of the quantities are relevant to this question. So be careful. And I think this is again a direct substitution question. So I expect very more answers in the chat. This time only if I get 5 or 6 people, let me see how many people are in the meeting. So there are 15 people in the meeting. Only if I get 6 answers will I move on to the answer and the next question. So please all of you do the question and answer the question. If anyone at any point does not understand or does not know how to do the question, I encourage you to put it in the chat or unmute and say. That is the right time to do it. And then, I can kind of give you some hint, or I can show you a relevant formula, and then you can try to proceed instead of me just showing you the answer straight away. So yeah, I encourage you to do that, because that is exactly what you'll have to do for your assignments. Okay, I see answers in the chat. C, Someone else also says C. Good. I want more people to answer. 531 kV, 531, 530. Okay, good. Good. I see more people are answering. Very good. I'll wait for 2 more minutes in case there are any more answers. Okay, I don't see any more answers in the chat. Rest of you who have not answered, do you have any doubt in this question or do you not know how to proceed? Please put that in the chat. I'll give you a minute. Okay, I don't see any responses. I think, yeah, I think maybe you are still solving or something. But okay, someone says don't know. Okay, so person said don't know. So here, what do we have to calculate? We have to calculate the Coulomb barrier, right? So how do you calculate the Coulomb barrier? What is a Coulomb barrier, first of all? We already saw the Coulomb barrier is basically this sort of repulsive force that occurs between two protons or whatever before they reach the attractive regime. So this is the formula of the Coulomb force, and this is just a direct substitution question. So are you familiar with Coulomb force of electromagnetism? Because otherwise, it's basically like your gmm by r squared in your gravity. Like that, there is a expression which describes the force between two charged particles, right? So Coulomb barrier is just a way to say that there is a repulsion which is happening between these two particles because of that force, and we have to overcome that repulsion, right? As I said in the before in the course, I mean before we did the problems, it's like when I bring two magnets together, there is a force which is pushing two magnets of same polarity. When I bring them together, there is a force which is pushing the magnets away. So I have to put enough energy from my hand so that I can push them together even closer, right? So similarly, the sort of force, the Coulomb force, is pushing away, and that creates a Coulomb potential, and that is often called a barrier, because it's actually acting like a barrier or a wall between the two particles getting together. So you just have to substitute the values into that formula, and that's how you get the value. So now can you just try it, and I will just move to the answer after that. Just try, because now it should be easier. Okay, maybe we have other questions, so maybe you can try it and you can verify the answer. But I hope you understood what I was trying to say regarding the Coulomb force, and now you understood how to do the problem. And others also, if you have doubt. So your friends were right. The answer is 531. Very good. So basically, as I said, the energy is Z1 Z2 E squared by R. Now, how do I find R here? Might be a good question, is how do I find R? So I already know that how nuclear radius can be calculated. So that's exactly why this R0 is given, and we have actually done this in one of the previous classes also, which is that that R is equal to R0a to the power of 1 by 3, where a is the mass number. So here I just have to substitute R in terms of that, and this is how my formula is. Now I have, this is my reaction, D plus P gives 3 helium plus gamma ray, and you can see that this is a deuteron is a hydrogen atom with one extra neutron. So the proton number is unchanged, it's still 1, but the atomic mass number for deuteron is 2, whereas for proton it's 1. And then if I substitute all those values and calculate, I will get 531. So whoever asked the question about not knowing the how to do the question, now is it clear to you how to do this kind of question? I think once you see this, it's a direct substitution. So maybe you forgot or you couldn't recall the R to R0 part or something, but whatever it was, you should have understood now. Yeah, good. So you know the thing. Okay, there is a typo here. There should not be any V here. Let me just remove that now itself. And also one thing I have to do is just put this here. This here. Okay. So sorry. I just remembered something that will come later. So let me just I'm showing all the answers, I think. Okay. I think I showed the answer by mistake, but it's okay. You still have to solve it. So this is again, this is the same question. The first question which you did, which was for the PP reaction, you have to find the gamma peak. Now for this reaction, D plus P gives gamma plus 3He, you have to find it. And this reaction is actually going to be what is going to, the questions, most of the questions we are going to solve is going to be of this reaction. So write down all the quantities that you calculate, because as I said, it might be the calculate quantity you're calculating in the second question will be used in the fourth question. So it'll be good if you solve all the questions, because then you will have a complete picture. So even when I was explaining the theory, I was telling you like this, because I have to calculate this, I have to calculate this, which means I have to calculate this. So all of them are connected. So it'll be a good idea that you write down the quantities and the values so that you can readily use them in the following questions. So this is the third question. Here you have to find the gamma peak of that reaction at the temperature. So again, this is exact dupe of the first question. So if you have done the first question and I've explained how to do the first question, you should do this very easily. So please put the answers in the chat. I'll give you a few minutes and I want a lot of answers this time. So again, you have to find gamma peak. And here also you have to find the gamma peak. So I'm just reminding you. So last time you found what is the Coulomb energy. Now you have to find the gamma peak. So yeah. I don't see any answers in the chat. I hope you're all solving the question. And that's why you're not answering. Okay, I see someone has given an answer 11.9. Others? I want at least 5 answers before I move to the next question. And we have a lot of questions, so please. Okay, I see. Oh, I see a different answer, 6.5. Okay, I see C now coming. Okay. Just okay. I think all the options have been guessed now. A, B, C, A. Yeah, I think I need more people to answer. Because there seem to be a variety of answers, so it'll be good if more of you can answer. Any more answers from the chat? Okay, one more A. 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 Okay. Okay, I see a lot of people saying A now. So I'll just move to the answer. The answer is A. So the rest of you, please check where you have gone wrong. My guess is you might have gone wrong in this step, which is a reduced mass. So again, it's the same exact formula. There is no change. So you know that this is a deuteron and a proton. So both of them have a proton each. So their atomic numbers are the same. But as I said, the deuteron also has a neutron. So because of that, the mass numbers are slightly different. So you know that the deuteron has a atomic number of 2 and the mass number of 2. The proton has actually, so I'm considering proton and neutron to have the same mass. It's an approximation. They're almost the same mass. So you can consider the mass of the deuteron to be something like 2 mp, whereas the mass of the proton is only mp. So that's why. And I can just solve it now also just to check if the answer is correct. To the power of 1 by 3. Yeah, the answer is 6.48 keV, which is approximately 6.5 keV. So I think many, if I'm not wrong, this should be the step where some of you might have gone wrong. So just be careful because we need both the mass number and the mass number and the atomic number, and they don't always have to be the same thing because neutrons contribute to only mass number and not atomic number. So just have that in mind. Okay, so is everyone okay with this? Anyone wants to protest or say that their answer is correct? Please, maybe I missed something in the question. Anyone like that? Okay, I think everyone's okay with this answer. So I'm moving to the next question. So now we want to find the width of the Gamow peak of that particular same reaction. So again, I showed you the formula for this when we discussed the class. So if you have the formula ready, it will be just a direct substitution. Okay, I see someone has already answered A. I don't know for this question or the previous question, but the chat just came for me. Others, please try putting the answers. Okay, I see someone says B. Others, please put your answers. I'm also doing it on the side. More answers in the chat, anyone? Okay, I see one more person said A. Someone else said B. I'll wait for a few more minutes for more answers in the chat. I'm just seeing if there's any more answers in the chat. I'll wait for two more minutes and then we'll move to the answer. Okay, I see one more person has said B. I think we can move to the answer. So, okay. Yeah, so the answer is B. I think many of you said B, few of you said A. So I'll just show you the solution. So this is basically I made a typo here. But let me just check if the answer is correct. One sec. Let's check what is the formula. It seems like the answer is not matching up, right? I just now saw that I made a typo. Uh, hmm. Am I missing something? Is it correct? Hmm. Okay, I think I'll just check this question. Anyway, meanwhile, those of you who have done it, just check the formula once. I think it should come. For some reason, now when I'm doing it, it's not coming. So yeah, point 0.7. Yeah, I know. I made a typo here. 0.749 should come. So if you put okay, we can move on. 15. Oh, okay. That's why. So I made some mistake, I guess, in the typing the formula. So what is the correct formula? Here it should be power of 5, is it? I see. Okay. So I think I copied the slide from the previous thing and I forgot to change the formula. So I'm sorry about that. So this is good. You guys are there to correct me. So I'll just make sure that I'll check the slides once more before I give it to you guys today. But yeah, if you put the correct formula, then I think it will come correctly. So yeah, cool. So that is the answer. So, now this is the next question. This is again based on the same reaction, deuteron plus proton. So here you have to find out what is the maximum value of the integrand. So here they have said something like factoring out the S factor. So I don't fully know what they mean by this, but in my understanding, you can just consider S of E to be a constant. That is how I did it, and you can also do it in the same way and see what is the answer you get. This is a little more tricky than the other questions. Not tricky, but you can try it. I think not tricky. It's actually a direct question only, but it uses those last few things that we discussed in the class. So please look at it, and meantime, I'll just check where I went wrong in that question. Okay, I see someone has said B. Any other answers from the chat? Okay, don't know. I see one don't know. I'll give few more moments for anyone else to try and then I'll explain how to do it. This is actually based on the Gaussian kind of thing that we looked at in the end. So maybe that's why it's a little difficult. Don't know. Okay, okay. I'll move to the solution. Just give me a second. I'm just seeing where I went wrong with that Gamow peak thing. Gamow peak using a Gaussian function, which is this. 0 centrum related to the width of the peak. Okay, okay. I'll see it later. Okay, okay. So I see. Okay. So first of all, they are asking you to find sigma v, right? Something related to sigma v. So we know this expression for sigma v comes to be something like this, right? So they are saying factor out s of e, and again I don't know what exactly that means, but I think s of e factoring out means that you set s of e to some constant and you're taking it out of the integral. We also see that we can now write everything in terms of some exponential function, and that makes it life easier when it comes to, and finally we get that sigma v is basically proportional to tau square e power minus t, where tau is this factor. So the integrand that you are left with finally is actually this e power minus tau. And you can try doing this on your own. When you do this derivation, you will find that everything comes out to be in terms of e power minus tau. And that is exactly, you can see that it's determinant, sorry, it's called as I max when you derive it as well, because it's the maximum value of the integrand. This is basically the integral from 0 to infinity. This will only be integrated and this gives a Gaussian, so it's going to go to 1. But this is a value which finally gives you the maximum value or the amplitude. So finally what we have to find is exactly that value which comes before it, and that gives us an answer of 2.93 times 10 power minus 7. So you can see that the I max is given by this expression. This is exactly a tau, and you know E0 is 1.22 blah 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 blah. So now if I put that here, I get that 1.22 times 3 by kt. All that if I substitute, this is the expression I get. So this is also a good expression to keep in mind. 42.46 z1 square z2 squared mu by t6. I have not written what is z1 to z1 z2 mu and t, because those have already been explained, because this is again the same reaction that we have been solving for last few questions. So z1 and z2 are 1, mu is 2/3 and t6 is 15. So if you take the value, this is the value you get. So does everyone follow this solution? Is everyone okay with this solution? Anyone who is not okay with it or has any doubt, please ask in the chat. Please put any questions in the chat if you have. Basically, this is also a direct question. You just have to think about it more in terms of the Gaussian. And that exponential function kind of tells you about the Gaussian itself. That's why. Anyone? Anyone having any doubts in this, or can we move to the next question? Please give me an answer so that I know that you are okay with it. No doubt. Okay. Okay, fine. I think if anyone has any doubt, we can look at it a little later. We'll go to the next question. Yeah. Okay. So again, we are looking at the same reaction, deuteron plus proton given helium and gamma ray. And you can see that they have given you the E0 value now, and they've given you temperature. And now they have not told you to factor out S of E, but they have told you to actually find it by giving you a functional form. right? Some function of E. And here B is basically a unit of area which is used in nuclear physics. It's called a barn. And yeah, one barn is something like 10 power, what is it, 28 or some minus 28 or something, 10 power minus 28 if I'm not wrong. Barn value, I'm sorry, I'm very bad with these kinds of numbers. Yeah, 10 power minus 28 meter square, which is basically the area of a nucleus, roughly, because a nucleus is 10 power minus 14 meters, and you can think of like that. It was called a barn because in nuclear physics that is kind of a big number, even though it's a very small number for us. I think it was something like, comes from the expression like, there's an American expression which is like missing something by a barn. Like a barn is a very big thing. A barn is some basically a building that is in farms and stuff. So it's kind of a big building which contains cows and sheep and cattle and all that. So when you miss something by a barn width, it's like you've missed the barn entirely. So I think that's where that name barn comes from. There's some sort of story like that, at least. So yeah, essentially barn is used for measurements in nuclear physics, similar to how AMU and those other units are there. So this is basically like meter square. So I just wanted to explain that. So yeah, reaction cross section, basically you have to find your sigma. So yeah, guys, please start doing it. I think sigma we have already seen how to find, so it should be easy and straightforward only. So if anyone has any questions, please put it in the chat, but otherwise you should try for a few minutes to solve it. If you're not able to, I'll show you the solution. Anyone trying to do this, or do you want me to go to the solution or anything? Please put it in the chat. Okay, I get one answer C from Swagatika. Anyone else? Any other answers in the chat? Or you don't know or something? Anyone else? I only see one person answering in the chat. Any other answers in the chat? Please put it. Okay, I see one more answer, C. I hope rest of you are also solving. I'll give you 2 more minutes and then we'll move on because we have to also wind up the session. Okay, I hope rest of you are solving. If you haven't been able to solve, you can see the answer. So the answer is, okay, sorry, one sec. Yeah, sorry. So the answer is C, like your friend said, very good. So basically, this is direct substitution again. This is your 2 pi eta and then S of E 1 by E. So instead of B by root E, 2 pi eta, again, as I said, it is like writing 1 plus 4 and 2 plus 3 for 5. They both are the same thing. But I guess 2 pi eta is what you used in your class with sir. So this is probably, more familiar to you. So 2 pi eta can be written in this form. Again, this comes from substituting all the relevant constants. Mu you already know because this is the very same reaction we have been doing again and again. So this is D plus P, which gives a mu of 0.667 or 2 by 3. E is 6.5 and this was given in the question, but also you yourself have calculated it in the second question. And this gives you this value, and now you have to find S of E. So S of E, they've already given you this formula, and what you have to do is substitute the value of E everywhere. This is kilo electron volt. Why did I put, oh, sorry, yeah. So this formula is for mega electron volt, and we know our value is in kilo electron volt, so that's why there's a 10 power minus 3 term. If you substitute and you get, then it's a matter of just putting every value here, and then you will get it in terms of mega electron volt barn, and that is, oh sorry, I didn't write the millibarn here. This is 10 power minus 6 millibarn. So this is barn and this is millibarn. So just like how there's meter and millimeter, that's why it's like that. So yeah. So any question in this, any doubts in this question? Otherwise, we'll move to the next question because we have quite a few and we are running out of time little bit. So any doubts in this question? Please put it in the chat if you have any doubt or any issue with this. Okay, I don't see any questions, so I'm assuming everyone has understood. If you haven't understand, please stop me. I'm giving you this time for you to stop me if you didn't understand this. Okay, there seems to be nothing in the chat, so I'm moving to the next question. Okay, so this is again related to the previous question, kind of. Previous questions, I would say. What is the thermonuclear reaction rate per particle pair of the same reaction that we have been doing? So what and all have we calculated? We have calculated for that reaction the Gamow peak, the width of the Gamow peak, and then we have calculated the integrand which comes there, the maximum value. We have calculated the cross section, and now we are going to calculate the reaction rate. So yeah, maybe some of the values you calculated before have to come here, so try to use that and do the question. So yeah, please put your answers in the chat. I will again wait for a few minutes so that you can have a idea to solve this question. So thermonuclear reaction rate basically means your sigma V term, which has been coming up again and again, right? So that's why it's mbcm per second, because that tells you that it's an area times a velocity. So sigma V, basically your averaged sigma V. So, sigma V, we have already actually calculated many of the quantities which are relevant to sigma V already. So you can try substituting those and see how the answer comes. So yeah, as I said, everything is linked. So it's better to, like, I think this is a good thing that they have done, like these NPTEL questions, which are all based on the same reaction. That's a very good thing because it gives you that context that all these quantities we are calculating, they all actually influence each other or they feed into each other. So that is the idea that's happening. So I don't see any answers in the chat, but I will wait for 2 more minutes in case anyone wants to answer. Okay, I see one person has said C. Any other answers in the chat? I will give you 2 more minutes to answer in the chat. Okay, one person says B. Any other answers in the chat? I'll give you one more minute in case anyone is still doing and wants to answer. Okay, I don't see any more answers in the chat, so I'll move to the answer. The answer is actually C, as I think one of you said. So again, this is coming from, this is a place where you have to put in all the answers that you did to so far together, because we are finally calculating sigma V, and you know that sigma V can be written as, um, exponential of this, and here this quantity can be written as I max into delta, because that we have already seen from the Gaussian kind of thing. So here by basically the multiplying and dividing by c squared, this multiplying dividing by c, this is basically so that we can write mu c squared as 931 MeV instead of carrying that mu as 0.66 AMU. So as I said, for the given reaction, we have already computed all the relevant quantities. You can go and check your previous answers. You have the Gamow peak, you have the maximum integrand, you have the delta, you have S of E, which we just now calculated, and then we also have this thing. So we put everything together, then we get this as the thing, and then finally we get 19.013. So is everyone following? Is this to everyone? This is again, this is just a place where we are putting together everything that we have calculated till now. So ideally you should have been following, so you should understand what has been done. So anyone has any doubts here? So this, as I said in this class also, we started with this expression and our goal was to calculate this expression. For calculating this expression only, we found Gamow peak, Gamow value, we found astrophysical S factor, we found so many things, right? So now in these problem solving also, we are following the same pattern. We have found Gamow peak, Gamow value, width, we have found the astrophysical S factor, we have found the maximum integrand when we write it as a Gaussian, and we are now putting everything together so that we can solve it in one shot. So is everyone's following this question? This question is kind of like what we did theoretically but in a problem format. So does anyone have any doubts or confusion relating to this particular question? It's very difficult for me if you guys don't respond. If you have no doubts, please write no doubts. So do you have doubts? Do you not have doubts? No doubt yet. Okay, nice. So you are able to follow this question. That means no doubt yet. Okay, good. Good, good, good. So even if you have doubts, this is the place to tell. Okay, so good. So again, this is just, these are all mathematical questions. You are calculating a few quantities and putting them together. Okay. So now we are doing in a sequence, so it's easy. But in exam, if you are suddenly given this or only this question, then you have to go back and you have to calculate all this. So please have that context, right? That everything is related, because that will be a good way to approach these kinds of questions, I think, for your exam perspective. Okay. Now, question number 8 is a little not so straightforward as the others. So I'm going to show you a quick derivation that can help you with this. So far we have been looking at the reaction rate in terms of the energies, and we've been looking at it in terms of the energies, right? But we can also look at it in terms of the temperature dependence. So to find the temperature dependence of the, so this is reaction rate per particle and this is Avogadro number. So this is basically the reaction rate of the entire distribution near some energy. If we look at it close to some energy, T is equal to T0, then you can look at it by introducing a power law. Okay, so instead of now having the variable be e, we are going to convert the variable to t, and now the t has some dependence using a power law. So power law is something like y is equal to x to the power of n. So here the question is to find that n. Okay, so this is yeah, this is not something that we've discussed so far, so I will just show you something that can help. So I've taken this from this website, and this is the one that I linked actually all the way um, in the beginning. I told you that you can look at this. So this is a PDF which contains actually all of the things we discussed with all the derivations. So I highly encourage you to look at the PDF and maybe derive with them what has been done, because that will be a good exercise for you along with doing problems to really have a feel for all these quantities like cross section, cross sectional area, reaction rate, all that. So yeah, basically the temperature dependence is encapsulated in tau squared e power minus tau term, which I showed you. Again, I'm going back and forth, so please stop me if you're confused. But as I said, after writing the integrand as a Gaussian, we can always recast it in terms of a new variable, which is e by t kind of variable, 3e by kt. Okay, so this contains all the temperature dependent terms, and that's why they have said that we are now looking at a power law for the temperature. So they say, as they say that, oh sorry, yeah. So temperature dependence is encapsulated in the tau square e power minus t term. And as I saw, tau is equal to e by t, which means energy varies, as you know, of course, t to the power of this. So we get, finally it's proportional to t power minus 1 by 3. So we want to approximate the reaction rate as a power law in t to set this as some power law. So the relationship is not a power law in general, because we also have this exponential of t term. So it's not just a power law, right? However, we can approximate the behavior if we are in the vicinity of a particular temperature near which tau is equal to something like this. So this is basically coming from your Taylor series kind of approximation. And what they have done is, you can look at this derivation in detail, because we are nearing the end of the class. I'm not going through it again. This is, again, as I'm saying, here there is no new physics. It's all based on your same reaction rate, same Gamow peak, same everything. They are just writing it in terms of some different numbers or different variables, so that we can see the temperature dependence better. So here it's more of a mathematical exercise, and I think you should all do it, then you will understand it better. So here they are trying to find the reaction rate, and its dependence by temperature, by looking at the slope in a log-log plot. So whenever you have a power law, if you plot a log-log plot, the slope gives you the value of the power index. So now this reaction rate is tau squared e power minus tau. So when you actually take the log and then do the derivative, you get that it varies as tau minus 2 by 3. So basically that means that your t power n is nothing but tau minus 2 by 3. So to do this question, what you have to do is, first you have to find tau. Tau is nothing but 3e0 by kt. And then you have to go and put tau minus 2 by 3, and then you will get the value. So this here the value, here the reaction is not deuteron plus proton, so be a little careful. It is alpha plus 12 carbon. Alpha is helium nucleus, carbon 12, and the reaction value is 200 megakelvin. So can you very quickly try to do this question, because I have given you how to do the question now, so I think you will be able to do it. You have to find tau, and then you have to find n, and n is equal to tau minus 2 by 3. Did everyone follow what I just said? Okay. I'll give you 2 minutes. We are nearing the end of the class. I don't want to hold you guys also too long, so that's why. Okay. 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 So yeah, good. You're following what I'm saying. So yeah, I'll just give you 2 minutes. Just try to find tau and give the answer. 17.6. Okay, someone has solved it. Anyone else? Okay, I'm going to move on because we don't have time, but please, all of you attempt it. The correct answer is 17.6, as your friend said. So, here again, it is just a straightforward substitution. Once you find tau, you just have to find n, and then, when you find tau, and then you have to find tau minus 2 by n, which comes to around 17.6. So, here again, be careful because for the given reaction, we don't have Z1 is equal to 1, Z2 is equal to 1 like before. Here we have a helium nucleus, which means atomic number is 2, a carbon particle, which means the atomic number is 6, and then each of their masses are different as well. So you have to be careful with the reduced mass, be careful the atomic number, rest of it is straightforward substitution. Is calculator allowed in the final exam? I am not sure. Can you please ask the NPTEL people? Like whatever, it will be communicated to you in detail, I think. But yeah, if maybe it should be allowed, I think. But just confirm with them once more because I don't do that, sort of exam and all those kind of. Uh, you can put it in the discussion forum. I'm sure they'll answer you. So you can try doing that. Okay. So yeah, the answer is 17.6. So yeah, just I would encourage all of you to go to this PDF. It's a few pages long, but it has everything related to Gamow peak and all these things, and including the derivations. So it's actually a very nice resource. I used it myself when I was making these slides. So I think it will be good for you if you look at that also. Because as I said, looking at things from different perspectives gives us a better understanding sometimes. Even though it has been taught to you in class, even though I said it, maybe looking at a PDF might give you more insight. So I'll go to the next question. The percentage change in the reaction rate of dp gamma, again our favorite reaction is back. That reaction at a stellar temperature of T is equal to 20 megakelvin. So here here it's kind of like an application of what you just now did. Just now what you did is you looked at the temperature dependence of the of the reaction rate, right? You looked at the temperature dependence of the reaction rate in terms of a power law. Here they are asking you how does that change with the temperature. So for that we have to do the same thing, but you have to find it in a slightly different way, the percentage change. So you know what is the rate at 15 megakelvin because that's what you were solving till now, right? You are solving for T6 is equal to 15. So you have all the quantities for 15 already. Now they are asking you when you compare to 15, so change, maybe I'll just change this like with respect with respect to T is equal to 15 megakelvin. Yeah, so yeah, 15 megakelvin you already know because you have solved all the quantities for that, including the cross section itself, I mean the reaction rate itself. So now they are asking what is the change in the reaction rate when we go from 15 to 20. So you have already found out how to find the temperature dependence from the tau factor. So use that and find the percentage change. Is that okay? So this is a little, maybe a little more indirect, but the previous way was a direct way to ask you the temperature dependence. This is an indirect way to ask you about the temperature dependence, but both the concepts are the same, the underlying concept. Anyone who has attempted this question? Okay, one person says E. Any other answers in the chat other than E, or maybe E again, anything? I guess B. Okay. Why guessing? Were you not able to solve it? No, I'm just kidding. Any other answers in the chat? I'll wait for one more minute and then we'll move on because we are actually at the end of the session. So I don't want to keep you guys too long. Okay, I think we'll move to the answer. So the answer is actually D. I don't know where you guys went wrong, but I'll just flash the answer here. So basically, you have sigma v. We just now found the n dependence, and you know that n is depending on tau minus 2 by 3. We already had t tau value. So from all that, you can find the uh, value to be 249. So I think this is also straightforward. Just check where you have gone wrong, if at all, and see if there's any problem. I think we can now. So is everyone okay with this? Is there any, have I made any mistake? Because before I forgot that t to the power 5 in delta, like I had just written the same formula as energy for delta also when I was making the slides. So I can make those mistakes because I'm also, learning some of this for the first time. So if I have made any mistake, please let me know. Otherwise, we can move to the next question. So this is the solution that I got. Any comments from the chat? Okay, I don't see any comments. I guess that means this is a okay solution. So getting it. Cool. Okay, so that's fine. So yeah, just check because these are highly mathematical, always the issue of careless mistakes and all happen. So please make sure make sure that you're very crystal clear with concepts so that conceptual errors never happen. Careless mistakes we have to do by solving lots of problems only. There's no other hope. But concepts, if you make clear, then at least you will not be confused about maths also, physics also. That's the issue. Okay. So final question for the day. And this is a theory question, so I want everyone to answer. Astrophysical S factor is more useful than cross section because one of these regions. So this I don't think you should take any time to answer because this is a theory question. Good, I see answers B, B, B. Any other answers or any other people to answer? Okay, very good. You should show the more same enthusiasm for problems also. But yeah, okay, good. I see a lot of answers. So yeah, you're all right. The answer is B, as I discussed. The astrophysical S factor is just a useful way for us to take out the energy dependence coming from quantum tunneling and from the size of the target due to quantum effects and all that, and just look at the energy dependence of the cross section, like pure cross section effects, and that makes it a little less sensitive to the change of energy. So that is why we use astrophysical S factor. So before I end, I had actually had a few extra slides. So the reason was that someone had approached me over the week. I forgot, I think Yuvraj or someone, and he had asked about how to study at IISc. So I had put the information here. Maybe next week, because today's class has already gone beyond time, I will not discuss in detail about it. But I have put a few links, and I've also put a few like posters that we made last year to talk about PhD and all that. So I actually wanted to ask you guys your background and then have a discussion with you, but I think now if we start that it will go even later. So I'll just flash the slides in front of you, and of course you can access the slides from the drive later to look at it as well. So yeah, these are all this is for school students, this is for your graduates and postgraduate students. So these are all made from IISc's open day posters last year, and that brings me to my final slide. So this Saturday 24th February is Indian Institute of Science open day, where all the departments open up their doors and we do various demonstrations and lectures. And the physics department and particularly the astronomy department will also be organizing some events. So if you are in the Bangalore area and you live nearby, I encourage you to come by, say hi, and go around IISc if you are interested in studying here and looking at all that. So I just wanted to give a small advertisement for this. So yeah, I think we can close today's session. If you have, as I said in the beginning, I will be, as we do every week, I'll be uploading the YouTube video and I'll be uploading the slides also. And apart from that, if you have any questions or queries, please mail me. I'll just go to the first slide. So this is my mail ID. You can mail me there. Some of you have been mailing me and I have been responding as and when I get time. This is my page where I maintain all the links. And if you want any particular topic to be covered, then please mail me in advance and I can cover that in the next session. So you can tell me about that. As I said, someone had asked me already about PhD and sort of opportunities at IISc and how to get into IISc. So if others are also interested in that, then maybe next week we can have a small session that is relating to PhD and opportunities at IISc and other places also, and I can tell you a little bit about my experience. So if you're interested in that kind of thing, drop me another mail. I'll try to do it here so that multiple people can do it at the like hear it at the same time. Okay, so I think we have already gone a little bit over time. So let's stop the session here. And if there are no more questions or immediate concerns, then we can stop it and we can meet next week. Okay, see you guys. Enjoy the rest of your week. Okay. Yeah. Okay, I'm gonna switch off and everything. Yeah. Bye everyone. Thanks.